As with propositional resolution, relational resolution works only on expressions in clausal form. The definitions here are analogous to those for propositional resolution. A literal is either a relational sentence or a negation of a relational sentence. A clausal sentence is either a literal or a disjunction of literals. And a clause is a set of literals, and as in propositional logic, represents a disjunction of the literals in that set. As with propositional clausal form, the empty set is also a clause. It's equivalent to an empty disjunction and therefore is unsatisfiable. The procedure for converting relational sentences to clausal form is similar to that for propositional logic. It goes by the catchy name of INCIDO, which is an acronym for the steps in the procedure. Some of the rules are the same as those in propositional logic. However, there are a few additional rules to deal with variables and quantifiers. In the first step, called implications out, we eliminate all occurrences of the implication and biconditional operators by substituting equivalent sentences involving only the and, or, and not operators. In the second step, called negations in, negations are distributed over other logical operators and quantifiers until each such operator applies to a single atomic sentence. The replacements here do the job. We eliminate double negations. We use De Morgan's laws to distribute negations over conjunctions and disjunctions. And we distribute negations over quantifiers. When this step is done, any remaining negations are applied directly to atomic sentences. In the third step, called standardized variables, we rename variables so that each quantifier has a unique variable. That is, the same variable is not quantified more than once within the same sentence. For example, in the case shown here, we rename the variable x in the second disjunct to y. In the fourth step, called existentials out, we eliminate all existential quantifiers. Now, the method for doing this is a little complicated. There are two cases. Let's take them in turn. If an existentially quantified sentence does not contain any free variables and does not occur within the scope of a universal quantifier, we simply drop the existential quantifier and replace all occurrences of the quantified variable by a new object constant. And by new object constant, I mean one that is not part of a language. The constant used to replace the existential variable in this case is called a Skolem constant. In the example shown here, we have replaced x by the new constant a, on the assumption that a is not already in the original language. If an existentially quantified sentence does contain free variables, or lies within the scope of any universal quantifier, there is the possibility that the values of the existential variable depend on the values of the associated universal variables. Consequently, we can't just replace the existential variable with a constant. So instead, the general rule is to drop the existential quantifier and replace the associated variable, this is not by a constant, but by a term formed from a new function symbol applied to the variables associated with the free variables and universally quantified variables in the target of the existentially quantified sentence. Any function this way is called a Skolem function. The example here illustrates the transformation and assumes that f is not part of the language. And in the case shown here, the existentially quantified sentence contains a universally quantified variable x and a free variable y. And so we create a term to replace the existentially quantified variable by taking f, our Skolem function, and applying it to x and y. In the fifth step, all's out, we drop all universal quantifiers, because the remaining variables at this point are all universally quantified, and we have only and, or, and not operators. This does not introduce any ambiguities, and it's logically equivalent to the original. In the sixth step, distribution, we put the expression into conjunctive normal form, that is a conjunction of disjunctions of literals. That's accomplished by repeated use of these 6 distribution rules. The first 2 allow us to distribute disjunction over conjunction. And the remaining 4 rules will just allow us to flatten nested disjunctions and nested conjunctions. And finally, the 7th step, called operators out. In this step, we eliminate operators by separating any conjunctions into separate conjuncts and by writing each disjunction as a separate clause. Okay, let's look at an example of this conversion process. Consider the problem of transforming expression shown here in the first line to clausal form. The expressions on the lines following the first line are the results of the various different steps of the in situ process. On the I step, we get rid of the implication operator. The N step has no effect since the only negation in the sentence is already applied to an atomic sentence. The S step also has no effect because there are no duplicate variables. Okay, now on the E step, we notice that the quantified sentence itself contains no free variables, so we can simply replace the quantified variable by a new constant. In this case, I've used Greg. The A step and the D step also have no effect. And finally, in the O step, we simply convert our conjunction into 2 separate clauses. Okay, that case was easy. Here's another example. Starting sentence is almost the same. The only difference is that we have a leading not. And the result is quite a bit different from the case without the not. Okay, as before, on the I step, we get rid of the implication operator. This time, the N step is more interesting. We need to push that negation sign down through all of the sub-expressions. So first, we distribute over the existential, flipping it to a universal and negating its target. We then distribute the negation over the conjunction, leading to a disjunction of negated disjuncts. We distribute the negation in the second disjunct over the universal quantifier, flipping it to an existential and negating its target. We distribute that negation over the disjunction. And finally, we eliminate the double negation. Okay, now the S step here has no effect, so we just skip past that one and get on to the E step. This time we note that the existential quantified sentence contains a free variable, and so we replace the existentially quantified variable not with a constant, but with a term consisting of a Skolem function, in this case h, and the free variable y. On the A step, we drop the universal quantifier. On the D step, we distribute the disjunction over the conjunction. And then finally, in the O step, we convert our conjunction of disjunctions to 2 separate clauses. Okay, in propositional logic, the clause set corresponding to any sentence is logically equivalent to that sentence. However, in relational logic, this is not necessarily the case. For example, the clausal form of the sentence, there exists an x, p of x, is the clause consisting of the single literal p of a, where a is a Skolem constant. And this is not logically equivalent to the original sentence. It's not even in the same language. Since the clause exists in a language with an additional object constant, there are truth assignments that satisfy the original sentence, but not the clause. On the other hand, the clause is effectively equivalent to the original sentence in the sense that it's satisfiable in the expanded language if and only if the original sentence is satisfiable in the original language. And as we shall see in resolution, this equivalence of satisfiability is all we need.